Yes, hi everyone, and welcome to Here and Now Online Services. So this is Maan, your online math tutor. So in this video, we'll be talking about a little of the trigonometric functions or the trigo ratios, but this talk is really for our sine function or the sine graph. This is our sine graph talk, okay? And yes, math learners and math teachers, we do have the similarity theorem for triangles, and having that in mind, we can say that in studying a triangle, we can define the dimensions or the sides of a triangle and its position in the Cartesian plane, okay, using the trigo ratios, okay, however small or however big the triangle is. Okay, so that's the beauty about the foundation, the fundamentals of trigo ratios. Okay, we can apply it to whatever fields, okay, to have that decent and very good sense of measure or good measure for good measure. Okay, and let me take this opportunity to update everyone that in my geometry Google Classroom, I have this new section, trigo ratios. Again, we have some suggested YouTube videos here. I researched it. I'll be adding more links, very beautiful GeoGebra links, okay, for better appreciation. Alright, and if you want to be added to this Google Classroom, just private message me, okay, or email me at anowen@gmail.com, and I will going to add you to this classroom for free. Okay, and you can consider also my services in facilitating it live, okay, to a certain class or to a certain math learner, and yes, I can be an online tutor that way. Okay, so let me now open one link here. This is this one. So GeoGebra link, and it's not authored by me. It is by our very own AYOOB. Okay, so we have the unit circle and the trigonometric functions. Okay, so this is a very beautiful build. Alright, and so we have here the graph of the sine function. Okay, and we all know that with the sine function we can have the opposite, the line, the y line or the sine line, that would be at the y-axis, something like that. So please to observe, okay, what will happen once we increase the magnitude of the angle. So we are still at the first quadrant here. So this is the sine line, the red line, and we also have the cosine line, the blue line, and we have the tangent line or the green line, right? So again, this is the first quadrant, and we have positive values because we have positive y, and our hypotenuse is also the positive side. Okay, and then we increase further the magnitude of the angle, and we are now at the second quadrant where our y is still positive, but it's now slowly decreasing in value, right? Okay. So yeah, 115 is the second quadrant, and we can still have a right angle there. Okay, so basically with the unit circle and the trigonometric functions, we are considering right angles, the study of right angles, right? Or right triangle, I mean. So let's now move or increase the magnitude further of the angle and move it at the third quadrant. So yes, the y value is now at the negative side. Okay, so you can see here that the sine, the value of the sine ratio is negative because y is negative and r is also you have here a positive value of y, so of r, the hypotenuse. Okay, so you have a negative value. Okay, and then let's now move to the fourth quadrant. Okay, so our y value is negative as well. Okay, but it's increasing again, going to the 360 degrees or the 0 degrees. So there you have it. This is a period, okay, of the sine graph. So a period is the whole cycle, the whole high plus the low of the sine wave cycle. So this is period. Okay, and then the half of a period is what we call as the amplitude. Okay, so it can be the high amplitude or the low amplitude. Okay, and we're not really focusing or touching much yet in this video the cosine function, but I'll show you as well how the cosine function graph looks like. So let's increase the angle. Okay, going to the second quadrant, third quadrant, fourth quadrant, and the sixth. So the blue line is the cosine graph and the green is the tangent graph. Okay, so it is basically telling us how the ratio of the triangle behaves. Okay, sine is opposite over hypotenuse, and the cosine is adjacent side over hypotenuse, and the tangent is opposite over the adjacent side. Okay, so let's now focus our talk to the sine function. Okay, so I have here an outline. Okay, so this is a very beautiful reference, online reference, also by J. Wilson. So we have the sine graph. Okay, so this is an investigation actually on how the values or coefficients of the standard form of the sine graph behaves, or how these values influence the graph. So this is a standard form of the sine graph. Okay, so y is equal to a sine bx plus c. Okay, so let's first start with the letter A. Okay, so J. Wilson said it will describe the amplitude. So let's then show it. Okay, so we have here, okay, alright, so these are the equations that I prepared. So we have here GeoGebra, and then we have the calculator here. Okay, and this is, okay, the sine wave, and our A here is 2. Okay, So considering again the standard form, right? A. So before the sine function, you have the coefficient A. Okay. So let me show the axis and show some grid. Okay. So as you can see here, the A describes the amplitude, the height, and the depth of the sine wave. So as you can see, okay, we have here the max, how high the wave will go, and how low and how deep the wave can go. So -2. The absolute value, okay, is 2, right? So A is the height or the depth of the sine wave. So is it really true? Then let's have this another example. So let's show this. See? So we're going to zoom this out to 6, right? So the maximum height is 6, and the depth, the maximum depth is 6, or the absolute value -6 is 6. So A again is the amplitude. Describe the amplitude. Next we have the B. Okay, so it will now describe the period. Alright, so I have here examples. Okay, that's a very beautiful ability of GeoGebra. There will be a slider. Okay, so again I'm going to show axis and show the grid. Okay, so as you can see here, okay, the bigger the absolute value of B is, the more narrower, or the narrower the waves are. Okay, and the smaller the absolute value of B is, the wider the waves, okay, are, and then the farther the waves are from each other. Okay, so here are another example. I have here 3. Okay, so I'm going to, yeah, that's 3, and for you to see the difference and for us to investigate. Okay, see, so 5 is bigger than 3, so it's narrower. The purple one is narrower. Okay, so that's for the period, the width and the narrowness of the period. And lastly, we have the C. And now we will going to describe the implication or the significance of the value C, okay, in the sine function, the standard form of the y function or sine function. Y is equal to A sine bx plus C. So what does C imply? Okay? So according to J. Wilson, C implies the phase shift. Okay, what do you mean by that? So without the C, for example, we just have y is equal to sine x. Okay. We can predict that the graph is going to start at the origin. Okay. So show the grid here. origin, and the sine wave starts at the origin. And now we were going to have C is equal to positive 2. Okay. Let's observe that the starting point of the period shifted 2 units to the left. So this is the green one. The green one is with C equal to 0. And with C equals to positive 2, the origin or the starting point of the sine wave shifted 2 units to the left. And that's 2 units of the whole sine wave. Okay? It's not the 2 units of the Cartesian plane, but a unit of the whole period. Okay, and the next one, we have this one. Y equal to sine x minus 3. So we have C equals to negative 3. So I'm going to write this. So these two observe that the starting point of the period shifted from the origin. It shifted towards 3 units to the right. Okay, so phase shift, the shifting of the starting point of the sine wave either to the left or to the right, depending upon the value of the C coefficient. Okay, so what would happen now if we have variations of A, B, and C? If we combine them, okay, can you predict how the sine gap will look like? Okay, so for example, this one. Okay, so let's just decipher it together without using GeoGebra first. Let's decipher it offline. So we have the height and the depth, so 4 units. Okay, and then we have 2, so it's a big number, so it could be narrow, it will not be that wide apart. And then 1, so it will shift to the left. Okay, a unit of the period. Alright, so let's now validate our assessment. So there you go. Height, the max and the mean. Okay, 4, and then 2, not so narrow and not so wide apart. Okay, and then 1, so from origin to 1 period unit to the left. And we have our final example here. And now we were going to have another investigation, another scenario. We have discovered a different variation, okay, of A, B, and C. So this is the equation that is being suggested by J. Wilson, this one. Okay, and if you would consider the initial assessment that negative 1 for C would mean a shift to the right, okay, and then a positive value of C would mean a shift to the left. Okay, with this example though, okay, we have negative B. Okay, the behavior, the shifting varied. Okay, it's not the same when we have a positive value of B. Okay, so for positive value of B, okay, then the shift for positive C is going to the left, and then the shift of a negative C will go to the right. But if the B is negative, then yeah, this one negative, like negative 1/2, then it's different. So again, if the B is negative, then the shifting for the C goes like this. So for positive C, okay, it will go to the right, and then for negative C, it goes to the left if B is negative. So for better picture and for a better visual, so here's the example. So here we have B equals to negative 1/2. So we have a negative B. Okay, so this one is negative 1. Okay, so it's a shift going to the right. Okay, and then this one we have negative 1/2 again for B, so it's a negative value, and we have positive C. So it's a shift going to the right, positive right, and then this one negative C, shift to the left. Okay, then let's validate if it's consistent. So we have negative B here, negative 1/2. So this is the origin here, and we have negative 1 degree. Okay, so it will shift to the left. So there you go, 1 unit of the period. And then we have positive 1, so it's a shift going to the right. Okay, so there you go. All right. So that's the another variation. Okay, so again, if your B is positive, then the shifting is somehow opposite. Okay, so if you have negative C, then it goes to the right, and then if negative positive C, it goes to the left. And then, but if your B has a negative value like this one, negative 1/2, then for negative C, okay, it shifts to the left, and for positive C, it shifts to the right side. So that's it. It's so amazing. Alright, so thank you for Jay Wilson for sharing this online reference. Thank you. So that's how the values A, B, and C of the sine function dictates or influence the sine graph. Okay, it's so amazing, right? So each coefficient would somehow quantify, okay, the height, the width of the sine wave, and the shift, okay, the positioning of the graph in the Cartesian plane. Okay, so there's really a meaning behind those numbers in the equation. So that's it for now. So thank you so much for listening, okay, and for supporting Here Now services. And this is my one way of appreciating the great scientific work of our scientists across the globe, okay, in discovering and preparing the vaccine for our COVID pandemic. Okay, so yes, together as one global family, we will heal, okay, as one. So thanks again. This is Man, your online math tutor. Okay, continue to support me, sustain me, and for any marketing and selling requirements, I can be of help as executive assistant. And yes, you may also have me as your family online vendor for your supplements and skincare, personal care, home care. Yeah, that is to sustain. Okay, my advocacy of populating online math content, okay, made here in the Philippines. So thanks again, everyone. God bless us all.